Hello everyone. So today we'll see some properties of almost sure convergence. Let me revise the definition. We say that a sequence of random variables xn converges to a random variable x almost surely if modulus of xn minus x goes to 0 for every omega in n complement, where n complement is such that probability of n is 0. So outside a set of probability 0, x and omega converges to x omega. Okay, this is the definition of almost sure convergence. Now let us see some properties. First of all, how do you check almost sure convergence? Okay, there are a couple of conditions, sufficient conditions, which can be used for checking whether a given sequence of sets converges almost surely. So let me write the first one among them. So xn converges to x almost surely if sum over n going from 1 to infinity, probability of mod of xn minus x being greater than or equal to 1 by k, this is less than infinity. Means what? Basically, the series with these terms is convergent. Okay. Why do we go for such a condition? Because actually checking whether xn goes to x for every omega in n complement may be difficult. Whereas checking something like this may be easy. For example, we know that using Chebyshev inequality, we can find an upper bound for such type of probabilities. And if the series of those things converges, then by comparison test we can get convergence of this. Okay, hence it may be easier to establish almost sure convergence via this. Another condition is if xn and x belong to LR. What do I mean by belong to LR? Their rth moments are finite. So let me specify what I mean by that. So that is, expectation of mod xn raised to r is finite and expectation of mod x raised to r is finite. Then we can have another condition for checking almost sure convergence. xn converges to x almost surely if sum over expectation of xn minus x raised to r is finite. Okay, and it's enough if this happens for some r. It doesn't have to happen for every r. If it happens for even one r, it is enough for us. Okay, so these are two criteria which can be used for checking almost sure convergence. So given any new sequence, you can try to check convergence for either of these series, and if that convergence happens, then you can say that the sequence converges almost surely to x. Okay, as we can see, almost sure convergence is actually like a pointwise convergence, just that it happens outside a certain set of probability 0. Hence, it does have some properties which are similar to real sequences. So first one among them is uniqueness of limit. But of course, we can't say that the limit is completely unique. We will have to say the limit is unique almost surely. What do I mean by that? Let me try to state. So suppose xn converges to x almost surely and xn converges to y almost surely. Okay. In usual real sequences, we know that in such a situation, x and y are equal. So here we will say then x omega is equal to y omega almost surely. So x and y may differ on sets of probability 0, but other than that, they are equal everywhere. Okay. How do I proceed with the proof? Now first we have to remember two things. Both the convergences are almost sure. What it means is, of course we are going to assume that xn, x and y, everything is defined on same omega. So xn converges to x almost surely means there may be some set of probability 0. Let me call this set as say n1, such that outside n1 xn converges to x. Okay. Now what about xn converging to y? We know that again xn converges to y almost surely, so there may be some set n2 which may be either some part may be common or it may be completely disjoint also, that is also allowed, n2, such that probability of n2 is 0 and outside that it converges everywhere. So first of all we have to worry about the common region. Okay, so let me write. So what I know is mod of xn minus x. So given epsilon greater than 0, there exists n1 which depends on epsilon and omega, such that mod of xn minus x is less than epsilon for every n greater than or equal to n1 epsilon omega. Okay, and of course for every omega in n1, capital N1 complement, because outside capital N1 this happens. Okay. Similarly, given this same epsilon greater than 0, there exists n2 epsilon omega such that mod of xn minus y is less than epsilon for every n greater than or equal to n2 epsilon omega for every omega in n2 complement. Okay. So over n1 complement something happens, over n2 complement something else happens. So if I want both the things to happen, then I should take intersection of those two sets, right? But what is the probability of intersection? Now we know probability of n1 is 0 and probability of n2 is 0. Okay. So can I say that probability of n1 union n2 is also 0? So probability of n1 union n2 is probability of n1 plus probability of n2 minus probability of n1 intersection n2. Probability of n1 we know is 0, probability of n2 is 0, and probability of n1 intersection n2. n1 intersection n2 is subset of n1 and of course subset of n2. So it is smaller, hence its probability must also be 0. Okay. So probability of n1 union n2 whole complement, which is same as probability of n1 complement intersection with n2 complement, would be 1. Okay. So now let me consider omega belonging to this set. Okay. So for omega belonging to n1 complement intersection n2 complement, what would happen is, let me consider xn omega, let me consider x omega minus y omega. Okay. X omega minus y omega would be equal to x omega minus xn omega plus xn omega minus y omega. Okay, I am just adding and subtracting xn, but for which n? So what I'll do is I will define n naught as maximum of n1 comma n2. We had n1 n2 and we know that the things that we want happen after n1 and n2. So if I take n naught as greater of the two, then both these things, let me go and show you what I am talking about. Okay, so both these statements would be true if I take n greater than or equal to n naught, right? Because this is happening after n1, this is happening after n2, and n naught is larger of the two. So this we know by triangle inequality can be written as less than or equal to x omega minus xn omega plus xn omega minus y omega. And we know that this is less than epsilon plus that is also less than epsilon. In fact, if we want, if you don't like this, you can make it epsilon by 2 here. That is generally the trick that we use in real analysis. let me make it epsilon by 2 here, epsilon by 2 here. Okay, and hence this would become epsilon by 2 plus epsilon by 2, which is equal to epsilon. What does it mean? We are saying that mod of x omega minus y omega is strictly less than epsilon for every omega in n1 complement intersection n2 complement, and basically this happens for every epsilon, because given any epsilon this is true. So this happens for every epsilon. So Archimedean property tells me that if something is less than every epsilon, it must be 0. So x omega minus y omega must be 0. Hence x omega must be equal to y omega for every omega in n1 complement intersection n2 complement, and we know that probability of this set is 1. Hence we will conclude that x omega is equal to y omega almost surely. Okay, so what we have is the limit of almost sure convergence is unique almost surely. Okay, now let us worry about some other algebraic properties of convergence. So in real sequences we know that if we have two sequences, then their addition, subtraction, multiplication, division converge to the respective things of the limit. Okay, so do we have something similar here? So let xn omega converge to x omega almost surely, and y omega converge to y omega almost surely. Then we have xn omega plus or minus yn omega converging to x omega plus or minus y omega almost surely. Then xn omega into yn omega converging almost surely to x omega into y omega, and if the division exists, means if yn and y are non-zero, then xn omega by yn omega converges almost surely to x omega by y omega. Now how do I prove this? They are again going to use the fact that outside a p-null set, outside a set of probability 0, this is nothing but pointwise convergence, and pointwise convergence is exactly similar to real convergence. I mean convergence of real sequence. Okay, so we will use the same trick that we did in the earlier proof. So let n1 be such that xn omega converges to x omega on n1, and of course probability of n1 we were using n1 complement and probability of n1 is 0. Similarly n2 complement be such that yn omega converges to y omega on n2 complement with probability of n2 being 0. Okay, and now we will define, say, n complement as n1 complement intersection with n2 complement, and we have proved in the earlier proof that probability of n complement is 1. And because you know that xn omega converges to x omega on n1 complement, y omega converges to y omega on n2 complement, in intersection both these things happen, so they are like real sequences. Hence xn omega plus yn omega converges to x omega plus y omega for every omega in n complement, and we know probability of n complement is 1 because it's a pointwise convergence, it's a real sequence there. For every omega it's a real sequence, so it happens. Same way you can write for subtraction and multiplication as well as division. Okay. Now let me try and prove one more result. So we said about addition, subtraction, multiplication and division. What about continuous functions? Okay, so let xn converges to x almost surely, and let G be a continuous function, then can we say that Gxn converges almost surely to Gx? That is the question. Okay. We'll again use the fact that outside a penal set, it's just like pointwise convergence, and hence it's just like convergence of real sequences. So we know that there exists n such that probability of n is equal to 0 and xn converges to x for every omega in n complement. Okay. Now, so for a fixed omega, in n complement, this is a real sequence. Xn is a real sequence. And for real sequences and continuous functions of real sequences, there is a result that if xn converges to x, then for that particular omega, gxn omega will converge to g of x of omega for a fixed omega. What does it mean? It means that all those omegas for which xn converges to x, gxn omega will converge to gx omega. Okay, so if omega belongs to set such that okay, we know n complement. Okay, so if omega belongs to n complement, then for that omega, this thing also happens. Okay, so let me now define a new set M complement, which is set of all omegas such that gxn omega converges to gx omega. Okay, so it is set collection of all those omegas for which gxn omega converges to gx omega. What we know is, if xn converges to x, then this automatically happens. So if omega belongs to n complement, then it belongs to m complement also. So n complement is subset of m complement. As a result, probability of m complement would be greater than or equal to probability of n complement, which is already 1. Okay. Therefore, what we have is gxn converges to gx almost surely. Okay. So almost sure convergence is invariant under continuous transformation. This is what we will say. Let me repeat. Almost sure convergence is invariant under continuous transformation. So if you take a continuous function, you can still retain the property of almost sure convergence. Okay. We know that almost sure convergence is stronger, and hence almost sure convergence implies convergence in probability. The reverse way is true if we have monotone sequences. So in general it is not true. But if we have monotone sequences, then it is true. What do I mean by that? Let me state clearly. So let xn converges to x, let xn converge to x in probability. Okay, xn converges to x in probability. Then further let xn be a monotone sequence. We'll have to say monotone almost surely, means for almost all omegas it is monotone. Then xn converges to x almost surely also. Okay, so the reverse way implication in general is not true, xn converging to x almost surely. However, if you have a monotone sequence, then probability convergence can imply almost sure convergence. Is it okay? So these are some of the interesting properties of almost sure convergence. We'll stop here. Thank you.